When you're first starting out in FIMMWAVE, it's important to make sure you set up the cross-section of your device correctly. We don't want the boundary conditions of our simulation ever interacting with the modes we're trying to simulate in FIMMWAVE and also in its applications in FIMMPROP. In this video, we're going to look at an example of how we can optimize a cross-section to get the most from your compute power and not interact with the physics of what we're trying to simulate.
I'm here in FIMMWAVE now with a rectangular waveguide cross-section made from silicon, and I'm just going to go straight to calculating the modes of this to see if we can find the problem with how we've built this cross-section. So looking at this mode, I can double click here to see its properties. And to see how it's interacting with the boundary conditions, the most important tool for us is the plot section tool. If I click this, we'll be able to see the field, and if I just click in the center, we can see how it is evolving over the left and the right, the X direction, and up and down in the Y direction. So the first thing I'm noticing about this mode is that we've got way too much space on the left and the right. You can see that the field has dropped down to 0 and its gradient has dropped down to 0 way in advance of the sides here. So we'll be able to crop off at least 5 microns off this to save a lot of space there. Similarly, with the top of the simulation, we've got quite a lot of room, headroom at the top here, so we can probably cut off 0.5 microns here. And at the bottom, I'm a little bit suspicious that this mode is now being forced to 0 by the boundary conditions here. So we're going to add a little bit more bottom to the simulation to make sure that the mode isn't interacting with the boundary conditions of the simulation. So I'm going to go back to our RWG editor and let's see if we can act those changes. So firstly, we can do the left and right. We're controlling the widths of this simulation with these 3 slices. You can see these have been set. The first slice and the last slice, copies of each other, have been set to a width of 10. We said we could take a good amount off that, so let's take those down to a width of 5. And then we want to look vertically, so we want to look at the epitaxy structure. So I'll double click on that section to bring this up here. So I'm going to add on around 0.3. Let's bring that to an even 0.5 thickness on the bottom. And I said I could crop off around 0.5 from the top as well. So we've added on 0.3 to the bottom and taken off 0.5 from the top. So we can see we're a little bit more zoomed in now, but we've also changed how much we're etching this device as well. How much we're etching down here is defined by these numbers here. We had these set to 2.1 for the left and right and 1.3 for the middle, but we've changed the etch by about 0.3, so we just need to set these back now. So we're now going to etch instead 1.8 to get the same depth on the sides. And we'll just take this down to 1. So this should be identical in geometry to our waveguide before, but now we're just cropped in on the left and right, we're cropped in on the top, and we've added a bit more of this silica substrate to the bottom. So let's have a look at the results. And using the plot section tool again, I can see this field has now converged all the way down to 0 and its gradient has gone to 0. Same for the top, maybe we could take off a little bit more from the top as well. But the left and right also nicely converging down to 0. So I'm confident now that we're not interacting with the boundary conditions of the simulation. This isn't just applicable for looking at our waveguide cross sections, but as I say, an important part of simulating 3D waveguide devices using FIMMPROP's EME. So an example there on the left is an MMI splitter, sort of a Y splitter there as well. Now we might optimize the cross section on the left hand side, the correct width there, but not consider that we need to optimize the cross section on the right hand side. So if you have a Z varying structure, make sure that you're looking at the cross section for both ends of your device. We said in the introduction as well that if we're looking for the place where the field and its gradient go to 0, then if our field has gone to 0, it would be decoupled from any neighboring waveguides. This actually allows us to decide the widths of computational regions in empty FIMMPROP as well. So you can see here I've got this ring resonator and a zoomed in part here of the computational regions there. These two waveguide arms I have going into this larger computational region. In these two arms, if we have correctly set up the widths of their path computational regions, and the field is going to 0 at the edge of this region, then as soon as those computational regions would start to overlap, that would be the place we want to simulate their coupling with this larger spanning computational region. And so at the point at which correctly set up path computational regions touch is where we should set up spanning computational regions to simulate coupling.